Lecture 9. Structured Types and Mutability. The programs we have looked at so far have dealt with three types of objects: int, float, and string. The numeric types int and float are scalar types. That is to say, objects of these types have no accessible internal structure. In contrast, str can be thought of as a structured or non-scalar type. We can use indexing to extract individual characters from a string and slicing to extract substrings. In this chapter, we introduce four additional structured types. 1. Tuple is a simple generalization of string. The other three, list, range, and dict, are more interesting. We also return to the topic of higher-order programming with some examples that illustrate the utility of being able to treat functions in the same way as other types of objects. Tuples. Like strings, tuples are immutable, ordered sequences of elements. Immutable and ordered sequences of elements. The difference is that the elements of a tuple need not be characters. The individual elements can be of any type and need not be of the same type as each other. Literals of type tuple are written by enclosing a comma-separated list of elements within parentheses. For example, we can write t1, tuple 1, set it equal to simply an empty tuple. Tuple 2, set that equal to a tuple containing 1, the integer 1, the string 2, and the integer 3. And if we print those, it'll print this. Looking at this example, you might think that the tuple containing the single value 1 would be written 1. But, to quote H.R. Haldeman quoting Richard Nixon, it would be wrong. What a reference. Since parentheses are used to group expressions, 1 is merely a verbose way to write the integer 1. To denote the singleton tuple containing this value, we write 1 followed by a comma, even though it's alone inside the hug. It has to be comma followed. Almost everybody who uses Python has at one time or another accidentally omitted that annoying comma. Weak. Repetition can be used on tuples. For example, the expression 3 times the tuple containing the string a followed by the integer 2 will evaluate to basically having 3 copies of these concatenated. It'll result in a single tuple that has a followed by 2, followed by a, followed by 2, followed by a, followed by 2. Like strings, tuples can be concatenated, indexed, and sliced. Consider this tuple, that tuple. Print that tuple, print this tuple plus that tuple, rather concatenated with, print this tuple concatenated with that tuple, followed by a list containing one element, 3. Print this tuple concatenated with that tuple, followed by, slicing, that's right. The second assignment statement binds the name t2 to a tuple that contains the tuple to which t1 is bound, and the floating point number 3.25. This is possible because a tuple, like everything else in Python, is an object, so tuples can contain tuples. Say tuple. Therefore, the first print statement produces the output, an overall tuple containing first this tuple containing these 3 elements, followed by the float 3.25. Okay? You get it? You got that? Feel good about that? The second print statement prints the value generated by concatenating the values bound to t1 and t2, which is a tuple with 5 elements. it produces the output, this. The next statement selects and prints the fourth element of the concatenated tuple. As always in Python, indexing starts at 0, and the statement after that creates and prints a slice of that tuple, producing the output okay. A for statement can be used to iterate over the elements of a tuple, and the in operator can be used to test if a tuple contains a specific value. For example, the following code, in which a function called intersect is defined that takes in these tuples as its arguments, or sets them as their parameter, you know what I'm saying, colon. The docstring explains that it assumes T1 and T2 are tuples, and it returns a tuple containing elements that are in both T1 and T2. It does this by first creating an empty tuple called result, then iterating over each element in the first tuple, nesting this, checking, right? If element in is also in T2, then add to our empty tuple that element, making sure that it remains tupleistic by adding a comma. Tupleistic isn't a real word, by the way. I hope that didn't confuse anybody. And then returns result. And finally, if we print this intersect function call with these tuples passed in, we'll get a tuple that has a and 2 in it as its only elements, because those are the elements shared in the tuples. Multiple assignment. If you know the length of a sequence, e.g. a tuple or a string, it can be convenient to use Python's multiple assignment statement to extract the individual elements. For example, the statement x, space y equal a tuple with 2 elements in it. It will bind x to 3 and y to 4, or it will assign 3 to x, 4 to y. Similarly, the statement a, space b, space c set equal to the string with 3 elements x, y, z will bind first element in the string to the first variable listed, second element in the string to the second variable listed, so on. Now, this mechanism is particularly convenient when used with functions that return multiple value. Consider the function definition. Find extreme divisors. n1, n2 are its parameters. It says assumes that n1 and n2 are positive integers, returns a tuple containing the smallest common divisor that is greater than 1, and the largest common divisor of n1 and n2. If no common divisor is found other than 1, returns none. Okay? It creates 2 variables, minval and maxval, and it simultaneously assigns the values none and none to them. Then it iterates over for I in range 2 up to, but not including, the minimum value of n1 and n2 plus 1. And if integer 1 modulo I, whatever index variable it's at that point in the iteration, if n1 modulo I is equal to 0, and n2 modulo I is equal to 0, and if minval is equal to none, then set minval equal to y. Or if maxval equal y, or then set maxval equal to I, and then finally return minval, maxval. Cool, good, great. The multiple assignment statement, min divisor, comma space, max divisor, equal, find extreme divisors, 100 comma space 200 in parentheses. We'll bind min divisor to 2 and max divisor to 200 because of the math it did. Ranges and iterables. As discussed in section 2.6, the function range produces an object of type range. All, like strings and tuples, objects of type range are immutable. All of the operations on tuples are also available for ranges, except for concatenation and repetition. For example, range 10 with this slicing operation going on here. Wait a second. Damn it. I'm not actually entirely sure what's going on here. If somebody wants to explain that to me in the comments, that'd be great, but I don't think that's going to happen. Evaluates to 4. When the equal operator is used to compare objects of type range, it returns true if the two ranges represent the same sequence of integers. For example, range 0, comma space 7, comma space 2 equal equal. Range 0, comma space 8, comma space 2 evaluates to true because the two ranges do represent the same sequence of integers. They do? How is that the case? I mean, they represent the same series of integers up to 7, which this doesn't include because that's the stopping point there, but this does. What? Oh, right, because it's an increment of 2. So, this also wouldn't include. Okay. Good to go. Alright, however, range 0, 7, 2 equals range 6, negative 1, negative 2. This evaluates to false, because though the two ranges contain the same integers, they occur in a different order. Unlike objects of type tuple, the amount of space occupied by an object of type range is not proportional to its length. Because a range is fully defined by its start, stop, and step values, it can be stored in a small amount of space. The most common use of range is in for loops, but objects of type range can be used anywhere a sequence of integers can be used. In Python 3, range is a special case of an iterable object. All iterable types have a method, a dunder method, because of the double underscore, underscore underscore, iter, iter, underscore underscore, that returns an object of type iterator. The iterator can then be used in a for loop to return a sequence of objects one at a time. For example, tuples are iterable, and the for statement for element in a tuple containing the elements 1, the string A, 2, and a tuple itself containing itself 2 elements 3 and 4. This will create an iterator that will return the elements of the tuple one at a time. And it will ignore these little parentheses. I mean, just 1, 2, 3, 4, 5. Python has many built-in iterable types, including strings, lists, and dicts. Many useful built-in functions operate on iterables. Among the more useful are sum, min, and max. The function sum can be applied to iterables of numbers. It returns the sum of the elements. The functions max and min can be applied to iterables for which there is a well-defined ordering on the elements. I mean, if there's no rational way to discern what is the maximum or minimum value in something, then it won't work, you know. Finger exercise. Write an expression that evaluates to the mean of a tuple of numbers. I probably shouldn't have done that. I'm sorry if that triggered somebody's, like, genuine issues with eating disorders. Like, that's not a joke, I'm sorry. I'm just running out of things to do with my fingers there. And nobody's gonna watch these anyway, right? So it's an ethical question for sure. Lists and mutability. Like a tuple, a list is an ordered sequence of values where each value is identified by an index. The sequence for expressing literals of type list is similar to that used for tuples. The difference is that we use square brackets rather than parentheses. The empty list is written as an empty list, in other words, square brackets with nothing inside. And singleton lists are written without that oh so easy to forget comma before the closing bracket. Since lists are iterables, we can use a for statement to iterate over the elements in list. So for example, the code, in which we define a list called horrifically L, which contains 3 elements: the string I did it all, the integer for, and the string love. And if we say for E in L, print E, it will iterate through each element and print on a separate line said element. I did it all for love. Such a topical reference. We can also index into lists and slice lists just as we can for tuples. For example, the code L1, a list containing 3 integers, 1, 2, and 3. L2, a list which equals a slice operation performed on L1. If we say for I in range, the length of L1, print L1 at I index times L2 at I index. And this will produce 3, 4, and 3. Good. I mean, I get the gist of that, but I couldn't honestly explain that super well because I don't remember the syntax for slices and shit very well. Using square brackets for 3 different purposes: literals of type list, indexing into iterables, and slicing iterables can lead to visual confusion. For example, the expression a list that is 1, 2, 3, 4 next to what looks like a slice, or is it a single, yeah, right, and then 1, oh, what the hell's going on here, which evaluates to 3, uses square brackets in 3 different ways. What the hell? This is rarely a problem in practice because most of the time lists are built incrementally rather than written all the way out as literals. True dat. Lists differ from tuples in one hugely important way. Lists are mutable. They can be mutated. They can be changed. In contrast, tuples and strings are immutable. It cannot be changed, written in stone. Many operators can be used to create objects of immutable types, and variables can be bound to objects of these types, but objects of immutable types cannot be modified after they are created. On the other hand, objects of mutable types can be modified after they are created. The distinction between mutating that's what I said, an object and assigning an object to a variable may at first appear subtle. However, if you keep repeating the mantra, in Python a variable is merely a name, i.e. a label that can be attached to an object. Woof. It will bring you clarity. Jesus Christ, when was this written? Oh. Hilarious, and perhaps the following set of examples will also help. When the statements text assigned to a list containing the strings MIT and Caltech followed by ivies, a list containing strings of, the Ivy League motherfuckers, are executed. The interpreter creates two new lists and binds the appropriate variables to them as pictured in figure 5-1. Let's guess what's going to be in here. Wow. Yep, right on the money. My imagination is godlike. Two lists. The assignment statements. Univs set equal to a list containing texts and ivies, the lists, texts and ivies, and univs 1 set equal to a list containing sort of this, the full lists. See, these create new lists and bind variables to them. The elements of these lists are themselves lists. The three print statement, print univs 1, and print if univs is equal to univs 1, we'll print univs, then univs 1, and then we'll say that it is true. And notice that though we passed in only just the name of these lists when creating this list, that when the print function is called with univs passed in, it actually expands it, opens out, and shows us everything inside the lists inside the list. It appears as if univs and univs 1 are bound to the same value, but appearances can be deceiving. As figure 5-2 illustrates, univs and univs 1 are bound to quite different values. Yeah, just new lists, guys. Just new lists, okay? They just look the same. Jesus. That univs and univs 1 are bound to different objects can be verified using the built-in Python function id, which returns a unique integer identifier for an object. This function allows us to test for object equality by comparing their id. A simpler way to test for object equality is to use the is operator. When we run the code, which will test value equality, the result of calling the id function on both lists and checking if that's equal will test object equality. Univs is univs 1 also tests object equality. And if we print just the result of calling the id function on them, what we'll get: true, false, false, and then id of univs and id of univs 1. Now don't expect to see the same unique identifiers if you run this code. The semantics of Python says nothing about what identifier is associated with each object. It merely requires that no two objects have the same identifier. Notice that in figure 5-2, the elements of univs are not copies of the lists to which texts and ivies are bound, but are rather the lists themselves. The elements of univs 1 are lists that contain the same elements as the lists in univs, but they are not the same lists. We can see this by running the code, which will demonstrate IDs of univs at index 0 and univs at index 1, followed by ID. Oh no, sorry, that's just a string saying that this is checking ID. Yeah, that's what checks at index 0 and 1, and then checks at 0 and 1 of univs 1. We'll get 4 different numbers. Okay? They're different lists, folks. Why the big fuss about the difference between value and object equality? It matters because lists are mutable. Consider the code. Text.append the string RPI. The append method for lists has a side effect. Rather than create a new list, it mutates the existing list text by adding a new element, the string RPI in this example, to the end of it. Figure 5-3 depicts the state of the computation after append is executed. Okay. It does that. The object to which units is bound, did I say it's 5 in the morning? Is bound still contains the same two lists, but the contents of one of those lists has been changed. Consequently, the print statements, print, string unos equals, and then the variable unos, print unos1 equals this, will now produce unos equals this list containing these lists, unos1 equals this list containing these lists. What we have here is called aliasing. There are two distinct paths to the same list object. One path is through the variable text, and the other through the first element of the list object to which unos is bound. We can mutate the object via either path, and the effect of the mutation will be visible through both paths. So if you append something to one and call the second variable name, which is associated with the same thing, you'll see the change that you made to the first variable if they're aliased. They're both referring to the same thing. This can be convenient, but it can also be treacherous. Unintentional aliasing leads to programming errors that are often enormously hard to track down. For example, what do you think is printed by this shit? L1 set equal to a list containing an empty list times 2. Fuck. L2 is set equal to a list containing 2 empty lists. Now, for I in range, the length of L1, is that going to be 2? It's going to be, what is it? You know, come on. For I in range, length of L1. Append I to L1 at I. Or is it, does that mean, right? Yeah. Yeah, I think. Print L1 and L1, but L2 equals L2. It will print L1 equals a list containing 2 lists, each containing 2 elements, 0 and 1, 0 and 1, but L2 equals a list containing only 2, also 2 lists, but each of which contain only one value, 0 and 1 respectively. Take a second to think about that, so that I don't have to. Why? Because the first assignment statement creates a list with 2 elements, each of which is the same object, whereas the second assignment statement creates a list with 2 different objects, each of which is initially equal to an empty list. Finger exercise. What does the following code print? L1. No, L set equal to a list containing 1, 2, and 3. L.append L and print L is L at index -1. The interaction of aliasing and mutability with default parameter values is something to watch out for. Consider the code, where we got a function called append val. The parameter is val, list1 equal, oh yeah, and a keyword, it's a keyword argument. I got confused for a second there. List1, which has a default value of an empty list. We will append val to list1, and then we will print whatever's passed in here to this parameter, list1. Wait a second, why is this capitalized? Is that a typo in the code example? This would give you a name error, right? Because I don't. Append val 3. Append val 4. You might think that the second call to append val would print the list 4, a list containing the element 4, because it would have appended 4 to the empty list. In fact, it will print a list containing both 3 and 4. This happens because at function definition time, a new object of type list is created with an initial value of the empty list. Then each time append val is invoked without supplying a value for the formal parameter list1, the object created at function definition is bound to list1, mutated, and then printed. So the second call to append val mutates and then prints a list that was already mutated by the first call to that function. Well, just any subsequent calls would then add more to it. When we append one list to another, exempli gratia, text.append IVs, the original structure is maintained. The result is a list that contains a list. Suppose we do not want to maintain this structure, but want to add the elements of one list into another list. We can do that by using list concatenation, using the plus sign operator, or the extend method, e.g., here we make a list, here we make a second list, here we make a third list made up of the first two lists, then we print L3 equals L3, then L1.extend L2, print L1 equals L1, L1.append L2, print L1 equal L1. This will print L3, set equal to, or L3 equals 1, 2, 3, 4, 5, and 6. Okay, that makes sense. We concatenated two lists containing 1, 2, 3, 4, 5, and 6. But also L1, when we print, in the second print statement, printing L1, this is the same? And then after that, after this extend, where we extend L1 with L2, is just like having concatenated them two into a third list, okay? And then, if we append L2 to L1, which was previously extended already, then we get its previous state followed by the separate list, because that's been appended rather than extending. Let's now notice that the operator plus does not have a side effect. I'm still not clear what they mean by side effects. I mean, how are they side effects? It just like code does things. I don't, it's not pharmacology. It creates a new list and returns it. In contrast, extend and append each mutate L1. Figure 5-4 briefly describes some of the methods associated with lists. Note that all of these, except count and index, mutate the list. Okay, bada bing, bada boom. These are common methods associated with lists. L.append, with one parameter, adds the object e to the end of L. L.count, one parameter, returns the number of times that e occurs in L. L.insert, two parameters I and e, inserts the object e into L at index I. L.extend, with one parameter L1, adds the items in list L1 to the end of L, mutating that list. You know. L.remove e deletes the first occurrence of e from L, also mutating. I mean, I missed some of the other mutated, but we're good. L.index e, one parameter, returns the index of the first occurrence of e in L, raises an exception, see chapter 9, if e is not in L. L.I removes and returns the item at index I in L. It removes and returns it simultaneously. Raises an exception if L is empty. If I is omitted, it defaults to index -1 to remove and return the last element of L. L.sort sorts the elements of L in ascending order. L.reverse reverses the orders of the elements in L. Okay? Hope you remember all that. Cloning. It is usually prudent to avoid mutating a list over which one is iterating. Consider the code. Remove dups with two lists parameters. It assumes that L1 and L2 are lists, and it removes any element from L1 that also occurs in L2 by iterating over L1 and checking if that element found at that step along the way of the iteration is also in L2, then use the .remove method to remove that element from L1. We define two lists, 1, 2, 3, 4, and 1, 2, 5, 6, and call the remove deps function, passing in L1 and L2 as our arguments, and we will say print
L1 equals,
followed by L1. You might be surprised to discover that this prints L1 equals 2, 3, 4. Actually, yeah, I kind of am. What? During a for loop, Python keeps track of where it is in the list using an internal counter that is incremented at the end of each iteration. When the value of the counter reaches the current length of the list, the loop terminates. This works as you might expect if the list is not mutated within the loop, I see, but can have surprising consequences if the list is mutated within the loop. In this case, the hidden counter starts out at 0, discovers that at index 0 of L1 is in L2, and removes it, reducing the length of L1 down to 3. The counter is then incremented to 1, and the code proceeds to check if the value of L1 at index 1 is in L2. Notice that this is not the original value of L1 at index 1, because index 0 has been removed, right, i.e. 2, but rather the current value of L1 at 1, i.e. 3. As you can see, it is possible to figure out what happens when the list is modified within the loop. However, it is not easy. And what happens is likely to be unintentional, as in this example. One way to avoid this kind of problem is to use slicing to clone. That is, make a copy of the list and write. Who doesn't know what the fucking word clone means, but got this far into its textbook programming? The list and write for L in L1 at the slice containing the entire list. Notice that writing new L1 set equal to L1 and for L in new L1. This wouldn't solve the problem. Fucking hell. I don't even think that it would, so why are you... It would not create a copy of L1, but would merely introduce a new name for the existing list. Slicing is not the only way to clone lists in Python. The expression L.copy has the same value as L, a slice containing the whole list. Both slicing and copy perform what is known as a shallow copy. Sounds like my ex-wife. I'm kidding, I've never been married. A shallow copy creates a new list, never will, at this rate, and then inserts the objects, not copies of the objects of the list, to be copied into the new list. So the code in which this little singleton list is made, and then L1 is set equal to the list L, and then L2 is set equal to a slice of L1 containing the entirety of L1, and then L2 is set equal to a copy dot deep copy L1. What? Then appended to L is the value 3, and then print the f string L1 equals formatted with whatever the final value of L1 is, then followed by L2 equals, and replaced with the final value of L2. This will print L1 equals a list containing one element, a list which contains itself two elements, and then L2 is equal to a list containing one element, which is a list containing two elements. Because both L1 and L2 contain the object that was bound to L in the first assignment statement. Now, if the list to be copied contains mutable objects that you also want to copy, import the standard library module copy and use the function copy.deepCopy to make it deep copy. Jesus. The method deepCopy creates a new list and then inserts copies of the objects in the list to be copied into the new list. If we replace the third line in the above code by L2 set equal to copy.deepCopy of L1, then it will print L1 equals the same thing here, but L2 is set equal to a list containing one list, which itself contains only one value 2, because L1 would not contain the object to which L is bound. Understanding copy.deepCopy is tricky. If the elements of a list are lists containing lists, or in a mutable type, consider. Okay, consider that. The value of L3 will be, holy fuck, a doubly nested list containing one value, because copy.deepCopy creates a new object, not only for the list L1, but also for the list L1. What? i.e. it makes copies all the way to the bottom, most of the time. Why most of the time? The code L1 set equal to a list containing 2, L1.append L1. This will create a list that contains itself. Jesus, please us. An attempt to make copies all the way to the bottom would never terminate. To avoid this problem, copy.deepCopy makes exactly one copy of each object and then uses that copy for each instance of the object. This matters even when lists do not contain themselves. For example, say if we do something similar to the above, but where we make one list with one element in it, then we make a second list which has two copies of this formerly made list, and then a third list which is set equal to a copy.deepCopy of L2, which contains 2 copies of L1. And then at index 0 of L3, we append the value 3, finally print L3. It will actually just print a list with 2 elements, 2 lists, each containing 2, 3. How does this 3 get in here? Because copy.deepCopy makes one copy of L1, and it uses it both times L1 occurs in L2. Okay. Yeah. Okay, that sort of makes sense. It's good enough for 5 in the morning. List comprehension. List comprehension provides a concise way to apply an operation to the sequence values provided by iterating over an iterable value. It creates a new list, in which each element is the result of applying a given operation to a value from an iterable, e.g. the elements in another list. It is an expression of the form exper for elem in iterable if test. Okay? Got that? Evaluating the expression is equivalent to invoking the function in which we got a function f which has an expression as a parameter, an old list as a parameter, and a parameter called test with a default value of this lambda function, which takes in x and returns true. Okay, and we got new list and empty list. And for e in iterable, if test, which is a lambda function with a default value of 2, or true, but if test with e passed in is true, right, then new list dot append, and we will append to new list expression at e, or expression with e passed in, and return new list. For example, check out this bread. I baked this myself. Finally, I feel like I'm cracking the code of bread. You can't really see it very well because I have a shit setup. For example, e squared for e in range 6 in square brackets evaluates to a list containing 0, 1, 4, 9, 16, 25. E squared for e in range 8 if e modulo 2 is equal to 0 in square brackets evaluates to a list containing 0, 4, 16, and 36. And x squared for x in a list containing 2, the string a, and 3, and the float 4.0 if type of x is equal to integer. This will evaluate to 4, 9. So it'll iterate, I'll check over these elements, and if the thing that defines that x is an integer, then it squares it. Everything else is ignored. List comprehension provides a convenient way to initialize lists. For example, if in square brackets we put an empty list for underscore in range 10. So we'll generate a list containing 10 distinct, that is non-aliased, empty lists. The variable name underscore indicates that the values of that variable are not used in generating the elements of list, i.e. it is merely a placeholder. This convention is common in Python programs. Python allows multiple for statements within a list comprehension. Consider the code. L equals a list containing a tuple, x, y, and for x in range 6 if x modulo 2 is equal to 0, and for y in range 6 if y modulo 3 is equal to 0. The Python interpreter starts by evaluating the first for, assigning to x the sequence of values 0, 2, 4, and for each of these three values of x, it evaluates the second for, which generates the sequence of values 0, 3 each time. It then adds to the list being generated the tuple x, y, producing a list, a whole bunch of tuples, 1, 2, 3, 4, 5, 6 tuples, each of which contains 0, 0, 0, 3, 2, 0, 2, 3, 4, 0, 4, 3, respectively. Of course, we can produce the same list without list comprehension, but the code is considerably less compact. And we could just make an empty list and then for x in range 6 if x modulo 2 is equal to 0, for y in range 6 if y modulo 3 is equal to 0, L dot append x, y. Append x and a tuple containing x and y to list L. I still personally kind of like these, but it's probably just because I'm a newbie and it's easier to read. But the following code is an example of nesting a list comprehension within a list comprehension. Good lord. Okay, so it does the above, but all of them with a bunch of nesting. Except this prints a list with one element, which is itself a list containing the tuples above, okay? It takes practice to get comfortable with nested list comprehensions, but they can be quite useful. Let's use nested list comprehensions to generate a list of all prime numbers less than 100. Why not? The basic idea is to use one comprehension to generate a list of all of the candidate numbers, that is 2 through 99, a second comprehension to generate a list of the remainders of dividing a candidate prime by each potential divisor, and the built-in function all to test if any of those remainders is 0. Okay. And we can do that by making in square brackets, writing x for x in range 2, space 100, if all, the all function with this passed in as argument, x modulo y is not equal to 0, for y in range 3, x, if the output, the result of passing all that into the all function, if that's true, whatever, evaluating the expression is equivalent to invoking the function generate primes, where we have an empty list called primes, and we start out for x in range 2 to 100, is prime set equal to true. For y in range 3 to x, if x modulo y is equal to 0, then is prime shall be updated to false. And if is prime, which by default means if is prime is true, then append to primes the value of x at that point, and finally return primes. Okay. Finger exercise. Write a list comprehension that generates all non-primes between 2 and 100. Listen, some Python programmers use list comprehensions in marvelous and subtle ways. That is not always a great idea. Remember that somebody else may need to read your code, and subtle is rarely a desirable property for a program. Okay. Lecture 9 complete.